Hello, today I wanted to talk about oscillation and simple harmonic motion. So first we are going to start by defining oscillation. So an oscillation is considered to be the cyclical motion of an object around its equilibrium. And the time it takes to complete one full cycle, which is called one full oscillation, is called the period. And the number of period per second is called the frequency. So here we can see that this pendulum has no motion, and therefore it is staying at its equilibrium point, and it has no oscillation, while this one is moving because this one will have a restoring force towards this point, so the equilibrium, and this restoring force will always act towards equilibrium and will act in every pendulum or in every system where there is oscillation. And so what we call a full oscillation is going to be the time taken to go, an oscillation will be the object going to the other point and back to this point and back to the original point. So basically, if we call this A and the opposite point B, the period for an oscillation is the time taken to go from A to B back to A. And then we're going to talk about simple harmonic motion. So to have simple harmonic motion, you need a couple of conditions. First, you need to have no external force acting. The only force that is acting towards the equilibrium, and it's called the restoring force. You need to have a fixed cycle, which means that, for example, if you're using a spring like in the example under, you need to have no damping. It needs to be always the same distance for the oscillation, which will then create the same period for every oscillation. And you also need to have a constant change in the displacement, the velocity, and the acceleration. And we are going to see how to represent them just after. But for now, this is an example of simple harmonic motion in a spring. So you start by compressing your spring here. And then when you release your spring, it is going to go back to equilibrium. But due to the energy that it has, it is going to extend to this point. And when it's extended, there's going to be the restoring force that is going to act towards the equilibrium. So it's going to act towards the normal position. And once it is got back to this equilibrium position, it has motion. And with motion, it has momentum. So the momentum is going to push it back to compression. And this, if there is no external force, so if we are in simple harmonic motion, also called SHM, we are going to have this forever. Like, it's never going to stop. And we can represent the acceleration, the displacement, and the velocity by graphs. So here we have the graph of the displacement of a spring, for example, over time. So this is going to be like the extension, compression, and this is going to be when it's going to be in equilibrium, when it touches zero. Then you have the velocity. So the velocity is not in phase, which means that the period is not at the same moment as the displacement. So at the beginning, you're going to have a big velocity because it's at equilibrium point, and at equilibrium point, you have a maximum velocity. And this velocity is going to go down, down, down until you reach your maximum point, because at your maximum point, you're changing the side of the motion, the direction of the motion, and therefore your velocity needs to go through zero to then be negative. This is when you're going to have another time where it's going to reach equilibrium. And then you have the acceleration. And so the acceleration, as you can see, is perfectly not in phase with the displacement, which means that they have half of a period of difference between them. So here we can see that when it's maximum displacement, it's maximum negative acceleration. And so from this, we are going to be able to say that the acceleration is proportional to the inverse of the displacement. And with this, we can see that we can explain this by saying that the acceleration here is due to the force F equal ma, comes from Newton's second law. And we can say that since F equal ma and the force is always towards the equilibrium, the acceleration will also be always towards the equilibrium, which means that here when it is maximum extended, the force will go towards the equilibrium, so towards a compression, and the acceleration will also go towards a compression. And then from this we can deduce that the graph of the force over the displacement in a spring or in anything can result in a negative downward slope that is constant, that has a constant gradient, because the relationship is